So in principle, so far we have not distinguished several components of our gas. But essentially, we have mentioned moisture several times already, but in principle, we haven't very much distinguished the water vapor component. However, according to the theory of a composed system, if we have a multi-component gas, we can add up its densities. Let's say we have an n-component system, and that gives our total density. It's just a definition. So you can add up all the densities in our system, all the masses, and then we divide by the infinitesimal unit volume, and then we get this relationship here. So the masses is composed. And then we can divide this obviously by the total density, trivial. So that means then equals 1. And these components here, they have no dimension. We call them sometimes mass fractions. You can call them MI. The sum of them gives 1. It's just a redefinition. Instead of densities, we can use this redefinition as a mass fraction. There's this percentage. You know, the air can be, our air can be made of as nearly 80% nitrogen and then 20% oxygen and so on. So we can do this. The only thing that we want to distinguish right now, and that you know that air is made of many components, and it's usually considered to be a well-mixed gas, even though maybe sometimes it's important to know where these gases are for their radiative and other properties. But in particular for the water vapor, it's important that we know where it is. Because water vapor can condense into clouds and can cause rainfall and so on. So the only component we really want to distinguish today is the water vapor component. So in reality, what we want today is we want to say our gas atmosphere is decomposed of the dry component plus the water vapor component. And the two give us the total density. Or, if we think in terms of mass fractions, we have the mass fraction of dry air plus the mass fraction of water vapor is equal to 1. Whereas we know already that this is much larger than the mass fraction of water vapor. There's always much more dry air present in a volume of gas anywhere than there is the water vapor. So we want only to distinguish, we say this is a well-mixed gas, and we only distinguish the water vapor component. So this is the only thing we separate. We could separate many more, because we know our dry air is made of many more gases, but we keep them all together. We say this is one ideal gas or perfect gas. If we now look at the distribution of water vapor, of course we can measure this. We see this distribution here. And this is in gram per kilogram. So the values that we see, the red colors there, they go up to 20. So that's 0.02, 2% of the air at the surface. So this can go up to, in extreme cases, to 4%. So MV is kind of varying, typically, as you can see here, from maybe 1%, 0.01 to 0.04. It cannot be much more than this. So it's really the case that the dry component is much larger than this water vapor component. Can you guess why we see this distribution here? I mean, how does it look like?
There is more evaporation in
This is one hypothesis. We could have water vapor where we have a lot of evaporation. But actually, we will see later on that this is not the case. It's not the case.
looks like
It could be that we have, it could be that we have large water vapor exactly where we have a lot of evaporation. That's a reasonable assumption. But as you can see, actually, we can immediately show that that's probably not exactly the case, because this is the map of the annual mean and time mean evaporation. You see, the structure is completely different. It doesn't look like that. It's this map here. So there must be a different reason for this map here. Or what does it look like?
the surface temperature.
It looks like the surface temperature. Almost exactly like the surface temperature. It is high in the tropics, small in the polar regions, and then in the western Pacific, western tropical Pacific, larger than in the eastern tropical Pacific. So first order guess wise, so the surface temperature is determining our water vapor. Why do you think is the case?
Because of Clausius-Clapeyron
Yes.
equation.
Yes. The Clausius-Clapeyron equation tells us how much water vapor the air can maximum hold. It's true that it's not necessarily that the air is saturated everywhere, but still, in these regions here, we would never be able to hold this much water vapor in a volume of gas. Impossible. It would rain all out. There cannot be so much water vapor. And the same is actually true, I don't have this picture now here, if we go up in the air. The temperature drop with height will lead that these values are decay extremely fast with height. So our water vapor is, if we go already 5 kilometers, is much less than what we see at the surface. It's an interesting, very interesting property, this. It's the same reason why, for example, in summer, in Trieste, we can have much more rainfall in a short time than in winter. In winter you can have many rainy days and it rains all day long, but the quantities are relatively limited. In summer, the air can hold much more water vapor because of the high temperature, and therefore in a short time you can have much more rain falling out of convective clouds and so on. And this has also implications for climate change, of course. In a warming climate, this is one of the most robust signals in all climate change assessment. In a warmer climate, we can have more extreme rainfall. Because the air is warming up, can hold more water vapor, and we can flush this more water vapor out. It doesn't mean that it rains everywhere more, but there's this potential. Since warmer air can hold more water vapor, we have the potential, in case it should rain, to rain out much more water than in a colder climate. This is a very important relationship, this. So the equation that is governing this water vapor is a normal diffusion equation for water vapor. So the equation can be formulated as this. We have the total density times dm specific humidity, and V is the mass fraction of water vapor is what we call specific humidity, by dt is equal to minus the convergence of diffusive fluxes. There are no resolved fluxes anymore if we formulate it in this way. We use now another version where we get resolved fluxes in this version here, but in this version of the equation there are no resolved fluxes like in the continuum equation. Only this diffusive flux, convergence of the diffusive flux, plus source or sink terms. Source or sink terms, we can immediately think what it is. There's a conservation for water, so that can only be a condensation or evaporation that gives us sources and sinks of the mass fractions here. And this equation is often used if you think back to your atmospheric physics course. We can often assume that these terms are small as long as there's no condensation, and then we can make, as long as there's no condensation, we can make the assumption if we lift a parcel, its specific humidity is conserved. It's a conserved quantity. It's an important relationship. One of these few conserved quantities as long as we follow the motion. But of course then, if we lift the parcel high enough, there's condensation and then it's not conserved anymore. But we can try to evaluate then what the condensation rate is and so on. Now you will show in an exercise, it's really completely trivial, to show that this translates into this equation for the density of the water vapor. So the definition is here, no? It's just the total density times the specific humidity. It's just the definition of our mass fraction. So this can be easily shown, and then the equation looks a little bit different, gets this additional term here. I wonder if there is a mistake. No, that's correct, because we have the, okay, fine. The dimensions are correct, okay. So you will show this. And then what we sometimes do, in order to get now this equation that we want to use, is we integrate this equation vertically. In our assumption, we make it simple. We say there's a ground, there's no orography. Orography would make the calculation more complicated. We say we integrate from zero ground to essentially infinity, or where the air becomes extremely thin. And okay. Formally, we say infinity. So we do this integration. And then we can, of course, on the left-hand side, we can simply exchange these two, the integral and the time derivative. On the right-hand side, we can distinguish the vertical component and from the horizontal components and integrate out the vertical component of the total convergence here. So that leads us for this resolved advective term, we get just the vertical velocity. So this would be d by dz minus d by dz. W. And then if we integrate this in the vertical, dz, that gives us just this term in its borders. And the same is true for the vertical component of this term. We get also this component itself integrated out in the borders. And we keep the other terms as they are, as the vertical integral. Now it's very reasonable, well, it's a must to assume that the vertical velocity at the ground, we have no orography, that we cannot intersect the ground, so the vertical velocity is zero. And it's also reasonable to assume that the density as we go up of the water vapor goes to zero. So this term will vanish. This term here is interesting. In infinity we can say there's no diffusion of water vapor if our air becomes very thin. Nothing goes out from the earth in terms of water vapor. It's a very reasonable assumption. Everything remains in, also because the water vapor decreases so fast with height. There's no chance that the water vapor ever goes away from the earth. So this is a reasonable assumption. This diffusive flux is zero if we go high enough up. But at the surface, what is the diffusive flux at the surface? At the surface, the diffusive flux is just the surface evaporation. The connection between the oceans or land surfaces or lakes or whatever and the atmosphere gives us the possibility this flux there can be different from zero, and then it's the evaporated flux that we have that we have to parameterize or whatever, or we simply call it evaporation. It's a so far undetermined rate. If we want to model this, we have to devise some kind of parameterization. We could go to molecular formula again, but it will turn out again very difficult. If we want to use it in our models, we have to devise some evaporation. You can imagine what does some parameterization. What does evaporation depend on? In principle, we have discussed this already. Wind speed, for example. Evaporation depends on how fast the wind is over our surface. And also the difference between the humidity between the surface, where it's saturated, and the air, which is usually not saturated. The specific humidity difference between the two of them will give us the evaporation rate. At the surface it's easy, we simply can express this using Clausius-Clapeyron by the temperature. But in the air we have to take into account how dry or how wet our air is. So one could devise reasonable physical parameterizations of this. But for the time being we can simply call it evaporation. The vertical integral of the source term is just the rainfall that comes out of our clouds or whatever that we can measure at the surface. There can be, in theory, evaporation and rainfall formation at the same time. We don't care. In the end, we count only what we measure that is falling out. Rainfall could be created, and then some of it could evaporate again. So this is kind of a, if all rainfall evaporates, this is zero. And we have rainfall creation in clouds, in simple clouds that happens all the time. We get cloud droplet formation, and then maybe that evaporates again. Then there's nothing, there's no net change of the water vapor. What has been created is evaporating. But sometimes the rainfall reaches the ground, and it's falling out of the air. It's not, we don't have it in the air. Maybe falls over land. The land surface collects it in rivers. The river flow into the oceans, and from there it may evaporate, or it may evaporate locally from the land. Anyway, the precipitation that really falls out of our column is this integral over the source term. In this case, it's the sink term, the precipitation. So then we can reformulate this equation in a very simple way if we assume stationarity. We now assume, okay, we average over a longer time such that there's no local change in the system. Then we have to have some equilibrium. And this equilibrium states that all the rainfall that we measure has to come either from locally, and this is for every column and every place of the Earth, valid in that case, if we can assume that the time derivative is zero. The local precipitation has to come either from local evaporation or from what we call vertically integrated moisture flux convergence. There can be no other way. And this also means if we integrate this over the Earth's surface, clearly this term vanishes because of the closed system. And then the total precipitation has to be equal to the total evaporation in the long-term mean. There can be day-to-day small deviations from this, but overall whatever we measure in rainfall has to be evaporated at some point. This is the hydrological cycle, no, that we permanently have. Mostly evaporation over the oceans, but also over land. So this is this vertically integrated moisture budget. If we now look at distributions, we have done this already. Annual mean, time mean, evaporation, estimated from reanalysis data, from kind of close, very close to observed data, and rainfall data, which in this case is really observed data. We see, okay, we cannot make this integral in our heads. that this fits, but yeah. If it doesn't fit, I'm sure it doesn't add up exactly to 0, these two. Or one minus the others is not 0. I'm pretty much sure of that. But of course, this is a mistake of the measurements. And we know it has to add up to 0. But I'm sure if you really do the integrals here, there may be a small residual, which is then measurement errors. Both variables are very, very difficult to exactly measure everywhere around the world. I mean, we don't have rain measurements clearly over the oceans where most of the rainfall falls everywhere, so we have to make satellite estimates and so on. And evaporation, also very difficult quantity, because it's, even in the models, we cannot really measure, it's not really measured. It's a derived quantity actually. This is usually you use reanalysis as a measure to integrate observations into the model, and then the model kind of interpolates these observations everywhere. But for this quantity, there's no measurement, essentially. There are some measurements, but no standard measurements. So this is a pure model-derived product. The model has a good state of the temperature, and specific humidity probably close to the ground, good surface temperatures, and then the model has an estimation of what is the consistent surface evaporation. And what comes out is this value here. As you can see, where are the regions where we have maximum evaporation? It's not, as you have said, in the Western Pacific, where we have the largest specific humidity. And it's not in the Western Pacific where we have the largest rainfall. It's in the subtropical, essentially, subtropical regions, where we have the high pressure system. So large winds probably, also the trade winds are here. So large wind speeds, clear skies, dry air, leads to high evaporation rates. In the Western Pacific, not so much, even though the water is very warm, but the air is very moist. So the fact that the air is quite wet already reduces the evaporation there. And probably wind speeds are also some are smaller than in this region. So this comes out of this formula. And then it's clear that this is the source, this is the sink. The air has to transport this quantity. This is what's happening. The air, water vapor, is transported around using the advection equation. It's transported to the extratropical storm tracks. It's transported to the regions in the tropics where we have most of the rainfall. It's transported around according to either of these equations, either of these local equations. Advection, essentially, if we use this equation for the specific humidity, if there's no rainfall, and this diffusion term, this is the surface evaporation essentially, but in the regions in between, the advection of this quantity acts on this water vapor. It's moved around. Now sometimes it's useful to further distinguish, maybe at the moment it's not very clear why we should do this, but it's useful sometimes for the interpretation of rainfall to further distinguish these two components. Of course, the total divergence the horizontal, these are horizontal velocities, can be split up in these two terms. In rho, in this partial, the density of water vapor times the divergence plus the advection of this water vapor component. And it's useful to have this because this means for most cases we will find that this term is small compared to this term. This means whenever we have a horizontal convergence in the presence of moisture, there is moisture flux convergence and therefore a likely reason to have rainfall. if the evaporation is also small, let's say over a land region, whenever there's converging air, we expect rainfall. That's interesting because we also know whenever we have converging air, that air is likely to rise in a stationary state. And we know a rising parcel has the tendency for, at some point, for condensation to occur because of the fast temperature drop with height. So this is an interesting consideration. But there can, so this is most importantly the term. Whenever we have convergence of air in moist air, because we have to have some moisture present, that tells us that this term is different from zero, then there will be rainfall. But this occasionally also this term could be relevant. We have advection of moisture from a very wet region to a drier region. That can also increase our rainfall if we look locally. Now sometimes it's useful and for practical purposes almost when you will do this analysis, and if you stay in climate research, it's in the atmosphere at least, it's very likely that at some point you will look at the vertically integrated moisture budget. Then practically you often have to use the pressure coordinate system. You have to replace this vertical integral by a dP over G essentially. Because most of the data that we get is in pressure coordinates. And so, yeah. But then, because of the appearing row here, then you would have to use the specific humidity. It's even more convenient because this is usually the quantity that is provided in the data that you can have from observational data sets and so on. So you could simply do the vertical integral in the pressure coordinate system from 0 to some kind of surface pressure. Or practically sometimes you will integrate up to maybe 10 kilometer height. And up there's no moisture anymore. But this is equivalent to this equation here. So now we want to, this equation has many applications. Whenever you look at it rains in a region, you want to understand the rainfall anomaly in the region. Usually one hint what causes this rainfall anomaly is look at the vertically integrated moisture budget, because this should give us a hint, a clue why we get increased rainfall in a region. So now we will apply this equation to a true climatic feature, which is the Sahel drought. So very different from what we have done before. This is now one real phenomenon that has happened in the past. And later on we will use the moisture budget equation. So Sahel is interesting. This is a small figure. Let's see. The Sahel region, you know, of course, where it is. It's just this edge between the Saharan desert and the ITCZ rainforest zone to the south. This is a relevant region because rainfall is relatively scarce and shows a lot of variability. So the population, of course, is very much dependent on how much this rainfall is in this transition region. But it's also a nice region, of course, to live because it's not all jungle and it's not all desert. So, of course, it's a nice, in principle, a nice place to be. But people depend on rainfall, so it's a problematic region. So we are on the edge of this, between this largest desert of the world and the rainforest to the south. There are other deserts obviously too, but this is the Sahara is the largest desert. Now we want to look at this. If we now look at rainfall, you can imagine a desert is a desert because it doesn't rain much. So this is the rainfall map for that region. You can see this is now really is not a satellite derived data set, but it's a rainfall measurement derived data set, because we don't have anything over the ocean. Of course it rains over the ocean, but we don't have measurements there. So we are just for the time being just interested in this region. Of course you see the desert has no rain, therefore it's a desert. In the rainforest, of course, it rains a lot, but in this transition region, there's this kind of this gradient of rainfall. And this is the region which we consider. This is something that is sometimes used for models, or also for scientific investigations to investigate vegetation cover. It's not just you could use vegetation cover in percent. It varies between 0 and 1, obviously. But this is another quantity that is called leaf area index. Have you heard that? It's kind of used for to estimate the density of the leaves. Because we can have, even if the vegetation cover is just one value, there could be many leaves that evaporate, or there could be just that the coverage is enough to have a vegetation cover of close to 1. And so this is a measure that says how much leaf area you have per surface square meter. And so you can see this quantity varies actually typically between 1 or 0 and 5 or 6. So in those regions here, we have 6 times as much surface leaves. If we put them all together, then there is a square meter of surface. Really, so, but in the Sahel, again, there's this transition. No? And so there was an interesting, also for the population for sure, frightening. First look at some other statistics. This is actually the decadal standard deviation. So we filter the data decadally and look at the standard deviation, interannual standard deviation of this data for the rainy season, which is summer, JJAS in this case. You can see that even though the rainfall is relatively small there, the standard deviation on the edge here is still quite large. And this can be highlighted by the quantity that is called coefficient of variation, which is you take the standard deviation and divide it by the mean rainfall. That gives us how strong is the interannual variation of rainfall compared to the mean rainfall. And of course it highlights region with a relatively low rainfall. So you can see here that this, in the Sahel region, these values become larger because we have more variation of rainfall but less mean rainfall. So they stand out for this reason. Of course, in the desert we have a problem. If the rainfall is 0, we divide by 0. So that we've got undefined values. So you have to have a threshold for this calculation and say, okay, when the rainfall is lower than, let's say, 0.1 millimeter per day on average in this season, then we exclude that and say, just set this coefficient to 0. Otherwise, you don't get anything reasonable. Now, if you take the rainfall index in this Sahel box region, which is defined in the notes, and you look at the long-term time series, something very interesting has happened there. And this is, you take every year, just the JJAS season, and draw what was the rainfall. And there's this striking phenomenon that from the 70s onwards through the 1990s and even into the 2000s, there were very prolonged dry periods. So Sahel drought called. But before there were prolonged wet periods. Now the units here are millimeter per day. That doesn't look very much, but these variations are very heavy compared to the mean rainfall. So this is a very important deviations from the mean rainfall. Maybe in this region almost nothing, and in this region probably nearly double the rainfall that is usually in that region. And then if you filter the data with a decadal filter, so if you use a running mean, then of course you get a smooth time series that highlights this drying period that we had. Now it's actually recovering. The data set goes only here to 2000 something. If you do a drought longer, it would have been recovered. So people have asked, so what is this due to? There is very strange behavior if someone has experience with analyzing climate time series. Often you find much stronger interannual variations compared to decadal variations. Because one reason is that El Niño governs, for example, in the tropical regions very much our year-to-year variations, and El Niño has a much higher frequency, for example. ENSO has a much higher frequency than these decade-long drought events that we have. Now, by now, it's thought there's a theory why this has happened. And the main theory is that there is a sea surface temperature forcing of this. So El Niño perhaps contributes. But then in the Atlantic, sea surface temperature pattern in the Atlantic, who were at the presentation yesterday, they talked about the AMO or AMOC, Atlantic Meridional Overturning Circulation. Those slow variations can have an impact. The Indian Ocean also. It's thought that this is SST forcing induced, so the several ocean basins can act together to cause kind of drought and wet period. But that there is a local land surface and in particular vegetation feedbacks that can reinforce this phenomenon very much. So it's something that is induced from a teleconnection, but then the local surface feedback can play an important role.
So, this is for the Sahel?
This is the Sahel rainfall time series. Yes. So it's a box. It's a box that is defined. I should have drawn the box actually. So essentially 12.95 to 17.5 north. That is the box in the Central African region.
And SSTs are influencing those. Are they like bounded by ocean? Because I thought that they were inlands. How the SST was affecting that.
Yeah, so how the SSTs are affecting this, we just take the rainfall in this box, we measure the rainfall average in this box, and we see this time series. Now, from this you cannot derive that this has been caused by SSTs or whatever, we don't know. This is from other studies. Other studies have shown that this was rainfall. How can you prove this? You take an atmospheric general circulation model, force it with an SST, and show that you can reproduce this time series. This is the only proof. Or the other proof would be you take this time series, the more empirical proof that people of course have done first, when models were not there maybe. You take this time series and correlate this. You assume it's due to SSTs, and you correlate this time series with the global SST pattern. And if you see high correlation somewhere, it's an indication. It could be by chance, or if statistically significant, maybe it's not by chance. So you may find, a very high correlation in some ocean basins, and that gives you a hint. Maybe this ocean basin could be important to force Saturday rainfall. And then maybe you want to analyze this with a model. You take an atmospheric general circulation model, perhaps impose just that sea surface temperature anomaly in that region, and run it, and hopefully you get a result that is consistent with what you have found before, or you are unlucky and you give up.
Okay.
I have two questions. First one is, has this been correlated to a shift in the ITCZ?
Yes, this can also be interpreted as a shift in the ITCZ. In particular, the part of this is forced by the Atlantic meridional overturning circulation part that shifts the ITCZ to the north and to the south. Yes, they are very much related.
So that's a reverse feedback from the ocean to the atmosphere.
Yes.
Which changes the general circulation.
Yes. In fact, if you look at the now, what we do actually is we take this period and we take this period, and we say we want to look at the pattern. We take a long period, take the average rainfall, and a long period in this time, and take the average rainfall, and look at the difference, but at the spatial map. Maybe that gives us some more indication what has happened.
Yes. And about the leaf coverage.
Yes.
It seems that the model and the observations are quite different.
Yes.
Like here you can see green over Middle East
Yeah.
and Arabia.
Yeah, it's a bias. Yes.
That's normal.
That's a frequent bias in models, unfortunately. But in this model, maybe particularly, yeah, it's a problem. Not enough tuning. But yeah, no, it's a bias.
If you could show the map of the world, I think it's on page 4.
A map of the world?
The map. This one is really key. You see that in all positions where we have upwelling, we have a desert. If you look at America, if you look at Southern America, if you look at the Canary section and Africa, then the Bangula section and Somalia upwelling there.
But here we don't have a desert, right?
But there is no upwelling in that region. The Canary is up there around Morocco, I think. Then the Bangula down here in Southern Africa.
Here, cool SSTs.
Yeah.
Yeah, these things must be related to each other, right? I completely agree with you. This is so thinking of this, that this is summer season, and we have seen that in the summer season the high pressures were actually over the oceans. Remember that figure that we have shown, that this large-scale high-pressure systems. So that means we, if the high pressure is somewhere here, we would have northerly flow induced, and that would probably cause on one side the upwelling, the coastal upwelling here, that makes the ocean cold, but also brings drier air and sinking motion to this region. The same probably is true here. We have this high pressure system, and that kind of has the tendency to dry out here. Whereas here it was wet, and here it was wet due to the position of the high pressure system. Yeah, there's an interesting link. Yes, absolutely. So the desert will be related to the position of our large scale pressure patterns, and the fact that we have summer. And in summer we expect it to rain in the tropical regions in the northern hemisphere, but we have the high pressure here, makes it dry in this region here and wetter in this region here. But there are many other components that could play a role. We have a big land mass here lying around. We have strong monsoons here. Maybe they could impact this. But in principle, this is what we see more or less on a large scale. We have no deserts here because there's the high pressure over the ocean that brings in moist air from the south, whereas the high pressure in the Atlantic brings in dry air and sinking motion in this region and wetter conditions in this region. So North America is a very clear, you can see a very clear dipole. Also in this region we see this. It's more complicated because we have ocean in between, but it's wet here and it's dry here. So clearly this high pressure, the position of the high pressure system and low pressure systems, they are very important. Yeah. So it's not random that it rains or doesn't rain in the desert. There's a reason. The large scale circulation provides this feature. Okay, so we wanted to look at this pattern. So we take now the dry period minus the wet period. Want to get some more information. Look at local rainfall changes in this between these two periods. And this is now again a map of this in millimeter per day. You see this drying is extremely widespread. It's not just dominated by one region or the other. It's really a widespread drying throughout. Of course, it has to be there by definition. Because if we look at the time series, we know on average it should come out like this. But the pattern, of course, is not guaranteed. But it shows this widespread pattern. But on the other hand, you see also that to the south of it, there is more wettening. So there is this, we were talking about the shift of the ITZZ, perhaps, yeah. There's a component that the ITZZ has shifted to the south. ITZZ may shift to the south if it's cold in the northern part and warmer in the southern part. There's this ITZZ shift component that we can clearly see here. But clearly it's dominated by this drying. This wettening here, even if you take the whole average, there would be still a drying. It's not completely compensating. So people have investigated this. I told you, try to find out what this is, why this is happening. So I told you that it's probably SST force, but then feedbacks. And this feedback that has been proposed is okay. First of all, sea surface temperature is definitely an important forcing mechanism. But there have been other players that have been proposed. Aerosols have been proposed because aerosol variation can reflect, for example, if we have increased aerosol in that region, it's close to the desert, so it's likely to be influenced by aerosols from the desert, dust, that reflects more sunlight and can change the surface energy balance. So it's a very, very valid candidate for possible feedback, and many investigations have been done, and also land use. So if people who live there cut off the forest, that may have an impact too. So there are many more possibilities. The one that we want to investigate is, do I talk about the charming mechanism already? Is the one that the kind of the natural variability component of this. So we think there could be an SST forcing, and that is locally enhanced by vegetation, land surface and vegetation feedback, without taking into account the possible role of humans in this case, the direct impact of humans, and also ignoring the role of aerosols, which could still be present. What is done, and then in kind of models that try to investigate this, we have to, if we believe it's the coupling to the land surface, usually AGCMs, what do? They have to do something at the surface. Okay? If the soil moisture, for example, the soil can be wet. When it's raining, it gets wetter, and that can evaporate. We have parameterizations for all these things. But vegetation cover in most models is prescribed. It's taken from observations and prescribed. Keep the system as simple as possible. But there are models that try to model vegetation changes. And this is what has been proposed. The simplest equation that you can imagine is that the vegetation, V is here standing for vegetation, can grow if there is some dependence on the soil moisture. So if the soil is wet, vegetation can grow. It's a completely empirical relationship. There's some coefficient A, and this equation has been derived by comparing with observations, driving this model with observations and tuning parameters to get a realistic variation in distribution. And then there's some parameter here. L is this leaf area index that we have seen before, related to the vegetation cover itself. And kappa is a solar extinction coefficient from solar radiation, because vegetation also cannot grow if there is no solar radiation. Vegetation cannot grow. So if there's no solar radiation, this is 0. And also if there are no leaves, then this becomes 0. Then this whole term becomes 1, and then there's no growth of vegetation. This is just a decaying term. We say, okay, vegetation that is growing has a life cycle. If we turn off the possibility to have photosynthesis or moisture, then the vegetation with a time scale will just die. It's just if you take away this term here, the solution for this equation is just an exponential decay. Vegetation would just exponentially grow up. So you can devise more complex model, but this would be the simplest way to parameterize vegetation in a model. And you can try to couple this to your model, because your atmospheric model will provide you with rainfall at the ground. The rainfall can be integrated at the ground to create the soil moisture. And the soil moisture, what is needed to drive this vegetation model. And also the radiation that your atmospheric model can provide.
That's okay. Is the effect of shading?
This kappa?
Yeah, it's kappa.
Is just the combination of the solar radiation available and the absorption by the plants.
Okay.
Parameterization of the photosynthesis by the plants. So the simplest way to parameterize this. Essentially, it just depends on the availability of soil moisture and the availability of sun. Maximum is, of course, happening if there's a lot of sun and we have a lot of leaves. Then this becomes small, and then the vegetation growth just depends on the moisture availability. So this equation has some physical, this is physically reasonable, but it's completely empirical. This is not a physically derived, it's not the Navier-Stokes equations. It's just an equation that kind of a physicist would invent to kind of parameterize the effect of radiation, solar radiation, and water availability on vegetation growth. But it's completely empirical. But this is done. So then people simply often relate the leaf area index to the vegetation cover itself to make the system easier. So you can verify also that such an equation may be valid. And then, why is this important where is the main feedback to the atmosphere? The main feedback to the atmosphere is because of the albedo that the vegetation can cause. Because a vegetated region, as we have seen already, is darker and will reflect less sunlight. So in a vegetated region, we have more there's more possibility to absorb the available sunlight. Whereas in the desert region, more solar radiation is reflected. So there's an effect on the energy budget at the surface for the atmosphere. And also this can be parameterized in terms of albedo. In the model we have to have an albedo. In the simplest models, again, the albedo is just prescribed. In most of the GCNs, the albedo is prescribed consistent with the vegetation cover. Over the ocean, of course, the albedo is set to a value nearly close to 0. But over land surfaces, we have to use some observed estimate. Instead, in this model, we use, again, interactive. It's the only way, it's one way where this vegetation change can interact with the atmosphere. The other way is increased vegetation will increase evaporation also, but it will also change the albedo. And again, we have an empirical law here that you can verify by using observations of leaf area index and of extinction coefficient here, and of albedo itself. You correlate them and find this is a reasonable relationship. So you can see that this value varies between, if this is 0, then we get the desert albedo, about 0.4, which is the albedo in the desert, so a lot of radiation is reflected. Instead, if this term is 0, so no leaves, we get to an albedo of 0.08, which is about what we have over the ocean. So very dark rainforests would have the same albedo as the ocean, essentially. So this is the parameterization that is typically used. And this provides the feedback to the atmosphere. So when we model this, of course, we want to know, and you mentioned this already, how good the model is. And unfortunately, you've pinpointed it already. The model is not particularly good in terms of... The model is kind of okay still in terms of rainfall. It has the main feature, at least the desert is there, and the tropical rainforest rainfall is there. But then there are biases. So the rainfall extends much too far into the Saudi Arabia here, to the east. There are biases. But this is more visible actually. Sometimes, okay, if you just look at rainfall, you can be happy. But then you look at other quantities, leaf area index, the structure is okay, but then look at Saudi Arabia, yeah, terrible, absolutely terrible. So maybe I should have spent some more time to tune this model, but it's not so easy. Also, there may be some other reasons why the model, sometimes even the observations are not we cannot trust 100%. So sometimes, there are two reasons why the things do not match. In this case, I do believe that it's mostly the model that is wrong and probably the observations, okay. But yeah, this is what we have to live with. And then we can also check if the model reproduces this property that we have strong variations in the Sahel compared to other regions, and that's at least more or less the case. So does the model reproduce? Okay, this is just a sketch of this model. Usually we have an atmospheric model that is coupled usually to a land surface. It has to be always the case. We need always to know what is the evaporation from the land surface and what energy do we get from the land surface. But the dynamic vegetation is not necessarily the case. So we can just simply prescribe that. And of course, ocean, we could have a coupled ocean model to it, or we could simply prescribe the sea surface temperatures, the observed history. And that's done in this. So what does the model do? We run the model forced with observed history of sea surface temperatures, and the model reproduces something like the Sahel drought. That means that we have shown the only forcing in the model, there's no other forcing. In the real world, there could be anything possibly still going on, but for the model, we can control what is varying from year to year? The only thing that's varying in this model was the sea surface temperatures. So this proves that the sea surface temperatures had an impact on the Sahel drought. And you can also see now this dipole very clearly. This shift of the ITCZ becomes very evident if we look now at the, particularly over the ocean here, we can see this. And this has been compared with a model that is run in the same way, but we don't have interactive vegetation. So this possibility that the vegetation interacts is not there. We have simply fixed the vegetation to some climatological mean value to investigate if that's important. And the outcome is yes. So the Sahel drought is always there, SST-induced force, but is reinforced by land sea feedbacks. Because this is stronger than this and is closer to observations. So then Charney has actually proposed what is going on. Where do I write this here? Charney has proposed this idea that, oh, maybe it's like this. You induce a rainfall reduction in the Sahel region. Then what will happen? That reduces the soil moisture. That may reduce the vegetation. If we reduce the vegetation, we increase the albedo. Oh, if the albedo is increased, we absorb less solar radiation. And so we have less radiation available at the ground to create convective events. So that may reinforce the initial rainfall anomaly. So that's what Charney has proposed. So the reduced net radiation leads to less surface warming, and so less surface warming means also, if we think of the hydrostatic equation, that we may create a surface high pressure. We have colder air, high pressure at the surface. If we think of our Ekman pumping ideas, that would lead to surface divergence. And therefore, if we think of our moisture budget equation again, surface divergence would immediately lead to reduced rainfall again. So the initial reduced rainfall would be reinforced by this, what we call Charney feedback. In a sketch, this. So we have less rainfall, less vegetation, increased albedo, and that reinforces itself. He first speculated that the human-induced component may have created this feedback, but this feedback was then later found to be also relevant in reinforcing the natural-induced feedback. So if we look at these components now in the model, we can check this. Even in the observations, we could check this. Here we look at the model result. So in this period where we have this Sahel drought, there is less vegetation cover in that region. Yes, that has worked. And there is increased albedo. The albedo has increased. And that means there is increased albedo means that more radiation at the surface is reflected. So we have less available for rainfall creation. So the pieces of the Charney feedback, they seem to work. And then of course if we have a model where this feedback is excluded, then in the radiation we see nearly no signal, just some signal probably induced by cloud cover changes and so on. There's a small, okay, first now we come back to our moisture budget. So we now want to look at our moisture flux, vertically integrated moisture flux convergence. It's a rainfall can only be created by either this or by evaporation. For the Sahel, it's quite interesting to look at, to see that actually the local evaporation has quite a strong feedback. Accounts for not 50%, but for the drought. If you add these two, you get the total precipitation change. So this is at least 30 or 40% of the total Sahel drought. So the local evaporation change has also contributed, and that's also consistent with the fact that we have less vegetation, we have less leaves that can evaporate, leads to less evaporation. So the reduction of evaporation is actually an important component. But it's also interesting to look at the surface pressure response. So Charney hypothesis, a high pressure over the region where we reduce the rainfall. If we look what is happening in the model is, we see actually most of the high pressure to the north. So the dynamic response is a little bit more complicated than what Charney proposed. And so the high pressure is to the north of the Sahel rainfall. So I didn't make this calculation, but maybe I will do it in future. It seems that this other component may be important in this moisture flux convergence equation. It's not only the convergence and divergence of air itself, but it could be that it's becoming also dry here because we get advection of very, very dry air from the Sahara into the Sahel region due to the pressure distribution. So it could be that it's not only this local effect, but it's some kind of a little bit more, still quite local because this is just to the north of the Sahel. But it could be that this is actually inducing a gradient, the gradient in moisture and the advection of dry air from the Sahara is actually playing a role in this region. So there's probably something more to investigate still. I think I want to stop soon. So if we look now at the rainfall time series of the model and compare this with observations, we see, okay, the model does not reproduce the full magnitude of the observed. Of course, it doesn't necessarily reproduce the year-to-year variations. But more or less, the dry period and the wet periods are reproduced. And interesting, the model has also the tendency to have multi-year droughts. There are periods where for 10 years we don't have a positive rainfall situation. Instead, when you use the model without the interactive vegetation, we see it's much more, the energy is much more on interannual timescales. ENSO-induced probably, or other SST pattern-induced, or just random induced variations are much more dominant than in this simulation where we have this vegetation feedback that induces a low frequency time scale in this Sahel region. Okay, maybe we discuss this a little bit more on Monday because I have to actually run to the PhD defenses at the university.